Hi, my name is Nina and I'll be presenting Lab3 Magnetic Field of a Bar Magnet. A magnetic field is a vector field that describes the magnetic influence of electrical currents and magnetized materials. In everyday life, the effects of magnetic fields are most readily encountered with nearby permanent magnets, which pull on magnetic materials such as iron and attract or repel other magnets. Magnetic fields are surrounded and created by magnetized materials and by moving electric charges, or electric currents, such as those in electromagnets. Magnetic fields exert forces on nearby moving electrical charges and torques on nearby magnets. A magnetic moment is a quantity that represents the magnetic strength and orientation of a magnet or other objects that produce a magnetic field. A magnetic dipole is the limit of either a closed loop of electric current or a pair of poles as the dimensions of the source are reduced to zero while keeping the magnetic moment constant. The distance dependence of the magnetic field due to a small bar magnet. We were to compare observed values to predicted values derived from the Biot-Savart on- and off-axis equations. Interestingly, the experimental setup had to be set up specifically to compensate for Earth's own magnetic field to ensure it did not affect our data. The magnetic field of the bar magnet was set up orthogonally to Earth's magnetic field, so the two values were measured separately, but each still contributed to a net magnetic field. The materials of the following lab included a bar magnet, a smartphone with a magnometer sensor app, a ruler, and tape. The first section of the methods involved orienting the smartphone perpendicularly to the bar magnet. I placed the smartphone flat on the table and rotated it until the X component of the magnometer read as close to zero as possible, to align with Earth's north-south axis. I then placed the ruler along the bottom edge of the smartphone to align east-west. To find the phone's magnometer chip, I oriented the bar east-west on the ruler. I then slid the phone perpendicularly to find the position where X was a maximum and Y was a minimum on the magnometer. After rotating the phone 90 degrees, I moved the phone perpendicularly to find where the X was a minimum and where the Y was a maximum. I marked both locations with tape on the phone. The observed values were measured at a location that produced an X component value of 1,000 microteslas, 1.5 times 1,000 microteslas, 1.75 times 1,000 microteslas, and 2 times 1,000 microteslas. The magnetic field at each location was calculated and recorded. The following chart and graph displays my observed data points at various distances. From our observations, we can make the conclusion that when the magnometer is far away from the magnet, it measures a near-zero magnetic field in the X direction, and that as the magnometer moves closer to the compass, the measured X component increases. Assume the magnitude of the magnetic field due to the bar magnet is proportional to a constant multiplied by the power of the distance written as k times r raised to the n. By taking the natural log of the magnetic moment k and n, the plot of the values will give a straight line with slope n and intercept natural log k. From my observed values, my slope was negative 2.8 with a negative 0.26 intercept. The intercept will later be used in our computational model. To answer the provided questions, if the smartphone had not been oriented to compensate for Earth's magnetic north, our observed values and calculated values would be affected by mismatched axes. The bar magnet would have its oriented axis and magnetic north would have a different axis. Without matching axes, the values cannot correctly sum to a correct net magnetic field. If two identical bar magnets were stuck together end to end and ran the experiment again, the new observed values would be twice as great in magnitude. Now on to the computational model. This model was designed to calculate and plot arrows for the magnetic dipole in various places in relation to the bar magnet to represent the breakdown of the direction of its magnetic dipole. Some key points to take note in the code were that the magnetic moment was equal to the y-intercept of the graph obtained from our data. The magnetic field had to include the dot product of the magnetic moment and r hat. The on-axis calculation had twice the magnitude of the magnetic moment as the off-axis magnitude. The following represents the direction of magnetic field orienting from the bar magnet. You can notice that this orientation is similar to an electric dipole's orientation.